Today we're going to be talking about Bernoulli's principle. A lot of people freak out when they see this formula because it's massive, but it's really not too bad. The algebra is pretty nice, and for most of our problems, a lot of the stuff on each side is going to cancel out. So don't get worked up. It's going to be okay. Let's get started. Bernoulli's principle is about how when the velocity of a fluid increases, the pressure in a fluid decreases. Now, most of you are probably going to be saying, Mr. Gillum, that doesn't make any sense. It's moving faster through. It's going to be hitting the walls harder. But what this is looking at is the internal pressure of a fluid, so how well it flows against itself. Similar to viscosity, but this only works when we're at low viscosity. So let's go right into when it only works. We have to make assumptions when using Bernoulli's principle. And our assumptions are that we have laminar flow. We have an incompressible fluid. And that we have low viscosity. All right, so using what we've seen up here, that as the velocity of a fluid increases, the pressure of the fluid decreases. If I were to give you a pipe, here's my pipe. We got a big old area on this side, A1. Got a tiny area on this side, A2. Some pressure that exists on this side, some pressure that exists on that side, P1, P2. We have a velocity going in. We have a velocity coming out. Using what we've talked about with Bernoulli's principle today, and what you guys learned about volumetric flow rate and the equation of continuity from last time, I want you to go ahead and set up these inequalities here. We have A1, A2, V1, V2, and P1, P2. Using this, we can obviously, the area is bigger on the left. I want you to go, pause the video, take a second, fill out the rest of the inequalities, and we'll see how you did. All right, so based on this is like sticking our finger in the end of a hose. It's going to come out faster, so V2 should be higher over here. Then by Bernoulli's principle, it's going to be moving faster, meaning it's going to be having lower pressure. If you guys remember from the first video that we did where we had the fluids demos, we had the two pieces of paper. Watch what happens when I blow in between them. They squeeze together. Air is the fluid in this case. When I blow through it, the air is going faster. It's got a higher velocity, meaning it has a lower pressure. That's why you'll notice on the outsides there's more pressure because the air is not moving and they bend into touch. So let's look and see what this looks like when we put it into practice with the math. We've got some pipe here, area 1, pressure 1, velocity 1, at some height, H1 above the ground. We've got another pipe side up here at H2. We get some new pressure at some new area and some new velocity coming out. We're going to try and derive Bernoulli's equation. Now I want you to take a breath. This is going to be a lot of substitution. Don't freak out. The only thing that matters is that you see it can be derived, and in the end, you know how to use the equation. So let's start from the beginning. Some amount of work is being done by the water flowing in, and some amount is being done by the water flowing out. All we're trying to do right now is set up an equation that shows energy is conserved. This is a closed system, just like we were working with on the last set of notes. There's some amount of potential energy because it's above the ground in the first part, and it's got some kinetic energy because it's moving. The same thing is true on the other side. What we're going to do is go about individually solving for each one of these. We'll start with work, but we'll just go through systematically one by one to solve for them. We know that work is equal to force times distance. And from what we learned about with pressure, force is equal to pressure times area. We can just substitute that in there. We also know from basic physics that distance is just equal to velocity times time. So we'll go ahead and plug that in there. And what we get is that work is equal to PAVT. Cool. Take a deep breath. We're going to take a quick second to just... Okay, here we go. So the next thing that we've got is that using our volumetric flow rate, delta V over T is equal to AV. We're going to rearrange this just so that we're solving for volume. The reason why will be more clear in a second. So we rearrange, we get that V equals AVT. We know that volume is equal to M over rho. So let's come over here. Volume is M over rho. That's back from our density stuff. So we get this equation right here, that AVT is M over rho. So what we can now do is replace this in here. I know this is a lot, but just take a second. It's going to be okay. We get that work is equal to PM over rho. So if we come up here and plug it in, let's just write it out as we go. We get P1 M over rho, plus we'll get some other terms. We get P2 M over rho. Gucci gang. I'm going to erase this, so write it down if you haven't already. So potential energy, this is our second part here. Potential energy is equal to mgh, a lot easier. Kinetic energy is equal to 1/2 mv squared. So we can go ahead and combine it all up here. We get mgh plus 1/2 mv squared plus mgh. This will be height 1. This will be velocity 1. This will be height 2. This will be velocity 2. Cool. We've got the whole equation, but let's simplify it a little so that it's more useful for what we're going to be doing. First thing I want to do is get rid of the m's. I've got it in every single term. That just simplified it a lot. Next thing I want to do is get rid of this disgusting rho on the bottom. I'm just going to multiply each term by rho. When I do that, I get P1 plus rho g h1 plus 1/2 rho v1 squared is equal to P2 plus rho g h2 plus 1/2 rho v2 squared. Take a second. We did it. That's Bernoulli's equation. Process it, let it sink in. We'll get back to it in just a second. So why is this useful? Well, it helps you when you have problems like me where you have low water pressure and you need to figure out why. But it also is useful for the problems we're going to try out right now. Let's say I've got some pipe here, and it goes like this. Down at the bottom here, it's got a velocity of 0.5 meter per second. It's also got a pressure of 3.0 atmospheres. Up at the top here, one last thing. This has a 4.0 centimeter diameter pipe. Up at the top, our velocity that it comes out is what we're going to try and find. We do know that it has some pressure we're also trying to find, but one thing we do know is it has a 2.6 centimeter diameter. Normally, we'd be at a dead end. We've got two different variables, and for every variable, you need a new equation. Luckily, we learned the equation of continuity, so let's start off with that. In this case, I'd be like, crap, I've got two things, but I know I can solve for V without P, because with our equation of continuity, we have A1, V1 equals A2, V2. The area at the start is going to be pi times my radius. The radius of this is 0.02 meters squared times my velocity at the start, which is 0.5 meter per second. And at the end, I'm going to have pi, which should cancel on both sides. I'm going to have a diameter of 0.013 meters squared. Sorry, that's radius times V2. Notice, The equation of continuity, the amount of stuff flowing in to flowing out, doesn't care about pressure. That's just a physical fact of reality. The amount of junk I push into one end, if it's completely compressed in there, has to be the same amount that comes out in the other end. We have incompressible fluids, so it is. So good, don't need pressure. When we solve for V2, we get a velocity of 1.18 meters per second. One piece of information I forgot to give at the start is that this pipe rises 5 meters. Using all of that, let's go ahead and try and plug it into Bernoulli's equation, the monstrosity that it is. P1 rho g h1 plus 1/2 rho v1 squared equals P2 plus rho g h2 plus 1/2 rho v2 squared. Assuming this is a normal pipe in your house for water, let's go ahead and solve this. So pressure at the bottom, that is in atmospheres. We'll eventually need to convert that. But before we even begin, let's go about solving, getting everything equal to P2. So P2 is going to be equal to rho gh1 minus rho gh2. So what I'll put that as is P1 over here plus rho g delta h, because it's just going to be h1 minus h2. We should end up with a negative number for that, since we're going from that side, or this side up to that side. This one minus that one to clarify. And then now we'll have 1/2 rho, and in this case, since there's a squared, we can't break it up the same way, but we'll get v1 squared minus v2 squared. Going ahead and plugging that in, we get 3 atmospheres, so that's 3.0 atm, and that's times 1.103 times 10 to the 5th pascals per atmosphere. And that's plus rho of water, which is 1,000 kilograms per cubic meter, times 10 meters per second squared, times negative 5 meters. All right, we're almost there. Plus 1/2, 1,000 kilograms per cubic meter, times the square of, this is V1 minus V2, so 0.5 meters squared, that whole quantity squared. Whew, Bernoulli's equation is long. Plus 0. Change that, 1.18 meters per second, bracket, squared, parentheses. Whew, that's a lot. And I am writing sideways. Don't blame me. So let's come down here, plug it all into your calculator, try it out, make sure that you're doing order of operations right. If you're not, when you try this, make sure you ask me in class and I can look at it and see what you're doing wrong. But when you plug all of that in, I get about 2.50 times 10 to the 5th pascals, which is approximately 2.5 atmospheres. So you'll notice that your water pressure is slightly weaker up there, even though you shrunk the size of your pipe. That's a lot. Take a second, decompress. I know I'm saying that a lot with this one, but that's because this is a lot of information to take in. We worked through that one together. Now we're going to do some problems where we do separate, where you pause and try and work it out. In this new problem, you're going to derive an equation to solve for the velocity of water coming out of a spigot at some depth below surface. So here's our water spraying out the end. And what I want you to try and do is derive an equation for, let's call this guy down here V1. The rate at which the water is going down is V2. Let's say this is like a giant vat, sufficiently large that you can barely tell the water's going down. And that there's some height between these. This is H2 minus H1. It's the difference in height. So I want you to pause. Using Bernoulli's equation, try and derive an equation for V1. I'll be right back with how we do it. Did you actually try it? Santa knows if you're lying. Okay. One assumption we know right at the start, exposed to the air, exposed to the air. That means that P1 equals P2. Don't even have to worry about pressure. It's going to cancel out on both sides. Next thing we know is that this area right here, the area of the opening of the cylinder, is significantly larger than the area coming out here. Well, based on our equation of continuity, A1 V1 equals A2 V2, that means that the area of this one down at the bottom, basically 0, which means the velocity for this one, basically 0. We don't have to worry about this velocity. V2 is going to be so small, we don't have to worry about it. Because when we look at it in Bernoulli's equation, P1 rho GH1 plus 1/2 mv1 squared equals P2 plus rho GH2 plus 1/2 mv2 squared. Whew, sorry, not m, this should be rho. Okay. Notice, these guys cancel. If this number is V2, if this number is super small and we're adding it, that means this whole component over here is going to be small, especially if we square it. So we can ignore that. So all we're left with is rho GH1 plus 1/2 rho V1 squared is equal to rho GH2. Well, let's get this guy by himself. So we get 1/2 rho V1 is equal to, and this is going to be rho G H2 minus H1. And now let's solve for V1 by itself. We're going to cancel our rows. So we get 2G, sorry, this should be squared. We get 2G H2 minus H1, and we take the square root of this whole thing to cancel out the square. And this is what's called Torricelli's theorem, Torricelli's theorem. And basically what it's saying is that the velocity of the object coming out there, you guys could have done this with potential energy and kinetic energy. You'll notice this is literally just mgh, except for a given, like it's volumeless, because if I multiply by volume on both sides, I'll get mass. So for a given fluid, the amount of potential energy is going to be the amount of kinetic energy that it gains. From falling from here to here, all of that energy is just going to be converted into kinetic energy on the side. 1/2 mv squared, mgh. Cool beans. The last thing I'm going to ask you guys to do today is derive an equation for fluids that are just moving horizontally in a pipe. So that's where there's no change in H. So derive equation for horizontal fluids. So what that tells us, if horizontal, delta H equals 0, which means that potential energy 1 is equal to potential energy 2. Take a second, pause the video. We're going to use Bernoulli's equation to derive this, but pause, come back in a second, look at what I got. Okay, so basically all I did on here was get rid of the potential energy terms, and this is what I'm left with. Not bad at all, pretty neat. Next thing I want to talk about are just some pictures of what fluids look like. You guys ever wonder how airplanes can fly? They're really heavy. Normally heavy things don't fly. What they specifically do is when they make an airplane wing, this is going to be a side view of an airplane wing, is the top of the airplane wing has significantly more area to cover. So if we have air that's flowing over here, look at how much further the air on the top, the air on the top has to cover. Meaning, if we're keeping the same volumetric flow rate, this air on the top and this air on the bottom, the same amount is going over at a given time. It's got to be traveling a lot faster on the top. Well, what do we know about velocity as it goes up to the pressure inside of a fluid? It's going to go down. So what I get is that as volume is constant down here, pressure is constant, We'll call this P1, V1, P2, V2. V1 greater than V2, which means that P1 is less than P2. We have a huge area of this wing. A pressure difference applied to an area is going to cause a force, and that's what's going to lift the plane up. Pretty neat. You see the same kind of effect when you look at curveballs. So what they'll do is they'll put some spin on a ball, and when it comes here, this air has to resist because the ball's surface is causing friction on it. So you'll get faster moving air on this side over here, slower moving air on this side. So V1, V2, we get that V1 is greater than V2. And because of that, we get a pressure differential. P1, P2, we get that P1 is going to have less pressure than P2. So because of that, the ball is going to drift to the left. You also see this, it's called the Magnus effect, I believe, or Magnuson effect. I can't remember which one. I'll try to link a video in the description of it where I think it's Dude Perfect. They go up on the top of a dam and they just spin a basketball backwards, and you can see the pressure differential from one side to the other. It ends up hundreds of feet away from the top of the dam. So that's all we've got today on fluids, and I believe this concludes all of the fluids notes.